focus of this course is on the contemporary design and implementation of embedded system design. Students will use and become familiar with embedded system development environments, embedded system architectures, and issues unique to embedded systems. Laboratory work will be a major focus of this course.
Hey guys, my name's Leah Kronitsky and I was in charge of all the sensors that we used on the rover. We used a total of 10 infrared distance sensors on the rover, each one with the ability to detect an object between 10 and 150 centimeters away. We placed 2 sensors on each side of the rover with 2 additional sensors on the front center to use for ramp detection. The sensors were placed at varied heights for upper and lower limit clearance detection of the rover. The current video provides a 360-degree view of the rover so you can see exactly where all of the sensors are located. As you can see, the additional 2 sensors on the front of the rover that are used for ramp detection are spaced vertically. In this capacity, the 2 sensors will provide the same reading if the rover is approaching a wall, but will provide slightly varied readings when the rover is approaching a ramp, allowing us to differentiate between the 2 situations. Here's some information about how the sensors actually worked. The values you see in this bar show some typical sensor data when the rover is 12 centimeters from the wall. The first 2 values show data sent from a sensor on the front of the rover and appear in little endian format, so it will be flipped when we do the conversion below. If we convert this hex value into decimal, we get 1014. This corresponds to an analog voltage of 3.27 volts. Looking at the graph on the left, we can see that an analog voltage of 3.27 volts corresponds to an expected distance of about 12 centimeters. Since that's the distance between the rover and the wall, it looks like the sensors are working perfectly.
My name is Danny Dwongpachan, and I'll be talking about the components relating to the motor movement and communication of data. The rover master pick requests movement completion messages from the motor pick in the form of 3 bytes, a start byte, done byte, and end byte. The rover master pick looks at the done byte for either a 0 or 1 to recognize if the motor command is still in progress or has been completed, respectively. The rover master pick also requests sensor data in the form of 23 bytes from the sensor pick. Just like the message format with the motor encoder data, the sensor data payload starts with a start byte, followed by 21 bytes of data and an end byte. Whenever the rover master pick receives sensor data, it places the done or not done byte after the sensor data bytes, just before the end byte, making the complete message to be sent over UART as 24 bytes. These 24 bytes are transmitted via UART and passed through the Wi-Fi unit attached on the rover master pick to the Wi-Fi unit attached on the ARM pick. The message length the rover master pick receives from the ARM pick is shorter at 7 bytes and handled once it is received. The motor pick handles both I2C and UART communication as well, but is not as complex as the rover master pick. Through I2C, the motor pick responds to requests for motor encoder data and also receives motor commands from the rover master pick. Once the motor pick has received a motor command, the message goes directly to the motor controller to adjust the travel of the rover. Motor pick receives motor commands from the rover master pick via I2C, and once it does so, it sends a slightly altered message to the motor controller via UART. The message the motor pick receives from the rover master pick is 7 bytes long, a start byte, the message index number, the data type byte, direction, speed, distance or angle, and a stop byte. When the motor pick sends the motor command, it simply sends a message that is 2 bytes long, 1 byte for the left motor and 1 for the right motor. The remaining data bytes the motor pick received from the rover master pick are used to determine how long it should continue that command. On the motor pick, timer 0 is set to trigger with an external clock. This external clock is tied to the quadrature encoders attached to the wheels of the rover and triggers by rotational ticks of the wheels. Timer 0 counts the amount of ticks and compares this amount to the distance the arm or simulator wants the rover to move, and once the amount has reached the proper distance, the motor pick sends a stop command to the motor controller. What our team has implemented is the ability for the rover to travel at variable speeds, distances, and angles. By using a motor encoder, we are able to calculate with decent accuracy the distance that the rover has traveled. With this data, the ARM is able to update their algorithm with completion messages, and the simulation software is able to recognize where the rover has gone.
My name is Igor, and I was in charge of writing the ARM code and the ARM pick code. The ARM serves as the brains of the rover and remotely controls its behavior. It queries the pick over I2C for sensor data x times every 8 seconds by a changeable parameter. The ARM pick then responds with the sensor data if it has it or all zeros if it doesn't. The pick receives sensor data from the Wi-Fi over UART and is set up to transfer whatever it receives over UART to I2C in the hardware. The algorithm of the ARM is as follows. First, sensor data is received from the I2C monitor task, which automatically sends the data to a data conductor. The conductor class routes the I2C data to the appropriate message queue in the appropriate task. The sensor data is then sent to the sensors task from the conductor. This data is then converted into a distance representation for each sensor and sent to the locate task. The locate task maps the route of the rover and determines its location. It also sends commands to the rover.
Hi, this is Brian Hillenbrand, and I worked on the simulation. The simulation position is new this year, created to have a group member focus on the design of a simulation for both the rover and the ARM processor. The intent for the simulation was to serve as a tool for the rest of the group as they are designing their respective components, including the ARM processor, rover sensors, and rover motor. It was my goal to make the simulation as transparent as possible, acting as a complete system as seen by the attached component. This would entail processing data based on the information received from the attached component, receiving and transmitting data with correct message formatting and protocol, and responding with data that is accurate to what would be produced by the physical component it is simulating. In addition, I wanted to create an intuitive user interface, fully featured with control buttons, a display of data flow, and a display of the physical world. This would include a map of the physical environment, which was provided by the professor, position of the rover within the map, and a display of the live and past sensor data. The Wi-Fi communication formatting was made up of 5 parts: a header byte, which was FE, a message index number, a message type, a payload, and a tail byte, which was FF. This formatting will be gone over more in depth later on in the video. The Wi-Fi communication protocol for communication between the ARM Wi-Fi and the rover Wi-Fi, and also the simulation Wi-Fis, was carefully designed to provide accurate data transfers as well as a robust missed message and failure handler. On the ARM pick, a message is formed and written to the Wi-Fi, which sends the bytes to the other paired Wi-Fi. When a byte is received, it's put into a message buffer. When the header byte, which is FE, is received, the message buffer is cleared. This clears out any garbage data that may have been stored in the buffer, including data from pairing, data from the last message, or corrupted data. When the tail byte, FF, is received, all of the data in the buffer is analyzed. At this point, one of 3 paths is taken. The first path is the message index of the incoming acknowledged message is not a match to the message index that was just sent. This could occur for a few reasons, mainly that the message was not processed correctly on the rover, or the message was corrupted in either transfer from the ARM to the rover or the rover to the ARM. No matter the cause, you should send the exact same message again. The second path that it can take is that no acknowledged message is received. The ARM pick determines there is no message received when twice the time required for the process has passed without receiving another message. In this case, send the exact same message again. The third path that it can take is the message index of the incoming acknowledged message is a match to the message index that was just sent. This means that the rover has successfully received the message. The ARM pick is now ready to process the data received and send a new one. There are 4 message types that are recognized by the ARM pick. 33, which is a motor command acknowledge. 34, a moving status update. 35, done moving message. And A, which is sensor data. Depending on which message type is received, the ARM pick will know how long the payload length will be. 33, which is the motor command acknowledge, is going to be 1 byte in payload length. 34, which is the moving status update, is going to be 0 bytes. 35, which is done moving, is also 0 bytes. And A is the sensor data, which is going to be 21 bytes. This message, the sensor data, includes all the sensor data for every sensor, which is 10 sensors altogether. On the rover master pick, when a byte is received, it's put into a message buffer as well. When the header byte FE is received, the message buffer is cleared. This clears out any garbage, and then when the tail byte is received, which is FF, all the data in the buffer is ready to be analyzed. Currently, we only have one recognized message type, which is 32, and that represents a motor command from the ARM. However, by leaving the message type in, even though there's only one message type, it allows for future updates to add more message types, which makes it very flexible for future development. Immediately after receiving any message, an acknowledged message is sent back to the ARM. Finally, the rover checks to see if the instruction has been run yet, based on the message index number that is within the message. If it's already been run, throw that instruction out, and if it is a new instruction that has not been run yet, then execute it. We chose to use this protocol design because it provides good protection against missed and corrupt messages. If a message is lost on the way from the ARM pick to the rover will never process it, and the ARM will time out and send it again. This will continue to happen until the rover receives the message and acknowledges the message. If the acknowledged message is lost on the way from the rover to the ARM pick, then the ARM still times out and sends the message again. The rover will receive it, but it will know that it's already executed the command and will throw it out. It will, however, send an acknowledged message to alert the ARM of a successful transfer. If data is corrupt or not what the ARM expected, which in this case could be information exchange from device pairing, then analysis will not be triggered and the data will stay in the message buffer until a clear byte from a real message is sent to clear the message buffer. We decided that if a sensor message is missed by the ARM pick, it's not very important and does not require a resend. This is because it will receive a new set of sensor data very soon, which will render the missed data obsolete. Controls were presented to the user as a GUI with buttons for forward, backward, left, right, left loop, and stop. There were sliders available for choosing turn angle, distance, and speed. When the user selects a command, the turn angle, distance, and speed are sent as the values currently displayed. The map, as well as obstacles and rover, are drawn on another GUI. The rover location is updated in real time as the rover drives around, including vertical and lateral position and angle of the rover. Received sensor information is also drawn in real time. A line protruding from the rover represents the sensor reading. A blue X is drawn at the intersection point to show the edge of the physical object. This is very helpful when driving along a wall to show current readings, but also to draw out the wall. It will also draw out any obstacles that it finds. Finally, past locations of the rover are colored in light blue to show its driving path.